In order to create this system of equations, we had to divide the wing up into sections, or we need to divide the wing up into sections and decide how these horseshoe vortices are going to be distributed across the wing. Now, of course, they butt up against each other. We're going to place them along the quarter-chord line or the bound portions, and then these horseshoe vortices will butt up right up against each other. But we need to decide how we're going to distribute those. There's a couple different ways to look at this and some interesting things we can learn from this as well. So maybe the most obvious way is if we wanted to just do even spacing. We choose n number of horseshoe vortices and we space those evenly across the wing, and then we would put the control points right in the middle of each of those horseshoe vortices. And there's an interesting paper by Jackson Reed that suggests that if you do this, then you will get first order convergence, and that is the order of convergence tells you how quickly you will approach the correct solution. If you double the grid, if I keep doubling the grid, so if I start off with n equals 20 and then 40 and then 80. As I double it, do I cut my error in half? If so, every time I double it, if my error gets cut in half, then that's called first order convergence. And so we can continue to converge until the error in our solution is acceptably low. Well, it turns out, and actually this order of convergence is what we would probably expect from this type of a scenario anyway. If you just look at how we're let me just show a plot of the force as a function of span. Remember, we're assuming that the force is constant across, or the vorticity is constant across each of these horseshoe vortices. And so if I were to plot the force on this wing as a function of span, it might look something like this. Okay, so, and then I'll shorten this up here. Anyway, if my wing ended right there, and this was my wingspan there. Anyway, my force might look something like that, and you can imagine that this is really a first order solution because we're assuming that things are constant across these regions. And so as we refine the grid, our resolution will double. If we double the grid, our resolution doubles here, and we would expect a first order type of convergence for this representation of the force on the wing. Now another way to node cluster, and actually the way that Phillips and Snyder suggest doing that in their paper, is using cosine clustering. Okay, so this was we'll call this even clustering, and so another way is to cosine cluster. And basically what you do there is we say that we're going to divide this up in terms of theta instead of the actual location. So what we would do is start at the center and look at one tip and kind of go around in a circle here to the other tip where the one tip, so we'd say this is theta. So we'd go from 0 to pi. So here's pi and here's 0. And we divide this up evenly in theta, and for each of those locations, we draw a line there, and that becomes our the corner of one of our horseshoe vortices. And so what happens here is that the regions in the center get spaced out a bit, but then we get more points near the wingtips. Okay, so it kind of clusters near the wingtip, which is nice because those are the regions of high gradients. And so it turns out if you do this, that you actually get second order convergence. That's second order convergence. Okay, and that means that if I double my grid, my error actually gets divided by 4 instead of just by 2. And so we more rapidly can decrease our error by doubling the grid than we can with even spacing. Now, one thing that's maybe not expected is that you also need to cosine cluster your control points. So let me put these in a different color, but it's going to be, and actually let me just zoom in on on a couple of these. So if we look on the right-hand side and we have a horseshoe vortex that looks like that, and then they're getting smaller and smaller as we approach the tip. What happens is these, if you also cosine cluster the control points, what happens is the control points out in near the tip actually get set a ways off center, and then as you move towards the center of the wing, those control points are more centered, and then again, if we moved to the left-hand side, they'd get off center again. So that's kind of a non-intuitive, but if you also cosine cluster your control points as well as the horseshoe vortices, that gives you this second order convergence, okay? So I'll put a link to that paper by Jackson Reed below that looks into that. And that's just an interesting thing to note. You probably want to cosine cluster if you're going to use this algorithm. Now, there's one other thing that you actually probably want to do, and that is if we have some wing, and I'm just drawing straight wings, but you can imagine these have sweep or dihedral or whatever. Let's say we have a control surface. So you're probably, so we're going to get we're going to have high gradients in lift near that control surface if we have a deflection. And so what I actually like to do is I treat this as a separate wing section. So I'm going to have cosine clustering here. I'm going to have a section here that gets cosine clustered, and then a section here that gets cosine clustered. So each of these are treated somewhat separately, and so the user or your code somehow has to decide how to divide up the number of nodes for each of these regions. You know, if the user put in 100 nodes across this whole thing, maybe you just say, well, this is 40% of the span, so I'm going to put 40 nodes in here, and then maybe 20 in here, and then the remaining 40 here, something like that. So anyway, you kind of have to figure out how to divide up the nodes there. But I like to cosine cluster near regions of high gradients, which is going to happen whenever you have a step in your control deflection. And another thing you want to do is cosine cluster in the center, and that's because if you have sweep or dihedral, you can have step changes in properties near that center, or also high gradients there near the center of that wing. And so I actually treat these as independent sections. Each of these sections here would be independent. We'd have 3 again on the right hand side. So that's generally the way this is handled, at least with this numerical algorithm, is that you cosine cluster for each of these wing sections, and you divide those up for these different control surfaces and different lifting surfaces. Just one more comment on clustering that I want to make. So you know, it's really interesting that this cosine clustering is so effective. In fact, it can take it from first order to second order on a straight wing, and we'll talk about that here in just a minute in the next video about some limitations of this method. But on a straight wing, it will take it from first order to second order, if you go from this even clustering to cosine clustering. And we actually see similar behavior in when we look at a vortex panel code on an airfoil, that cosine clustering can significantly increase the accuracy or the convergence of the method. And I think that this goes back to the fact that for those who have learned about conformal mapping, you can map the airflow from a cylinder to the airflow around an airfoil. So there's this inherent relationship between flow over a cylinder and flow over an airfoil, and we can prove that in 2 dimensions. And in 3 dimensions, it may be something similar, but more like a flow over a sphere to flow over a wing. Not really sure. I've never looked at this in detail, but there's just this really interesting thing that happens with cosine clustering that we see not only for airfoils, but also for wings. And so that just leads me to believe, and because cosine clustering is related actually to a circle or a sphere here in 3D possibly, but because of that relationship, I just wonder if that's why the cosine clustering works so well, because the aerodynamics may be related in more abstract ways between flow over a sphere or a circle to flow over an airfoil and a wing.